I'm going to show you one of the tools we used in the design process of the A1, which is CFD, or Computational Fluid Dynamics. CFD is effectively a computer simulated wind tunnel. On top of measuring aero forces, CFD can also create these visual analysis to help us better understand how the shape of the car reacts to the air around it. So on screen now we have the A1. This is a CP plot over the top of the bodywork. So CP stands for coefficient of pressure. So anything in the orange and up into the red is positive pressure. Anything in the yellow and down into the blue range is negative pressure. So on the upper surface of the body, we're looking for the red to be pushing the car into the ground. And on the undersurface of the body, we're looking for the opposite to be true. So low pressure sucking the car into the ground. Force is equal to pressure times area in this scenario. So we have negative pressure over a very large area, 26 square feet, helping us to create the downforce that we need to make the car go faster. And we can compare our CP plot on the Revolution to one of a single seater. So it's a very similar trend we have on the upper surface. The front wing, front and rear wings has positive pressure pushing the car down into the ground. There's a little bit in the center of the car. On the main floor we have some positive pressure collecting. And on the underside of the car, very similar. We have big negative pressure on the front wing, and the whole of the underfloor is negative pressure and sucking the car into the ground. As well as the static pressure acting on the bodywork, we can see the airflow working dynamically around the shape of the car. So this is a section we're cutting through the vehicle's shape. We can see the vortex appearing from the front dive plane as the bodywork appears. Then we can see as the tub starts to expand, we have this high energy airflow working through the car and helping to push out this dirty air from around the suspension, which is also then caught by the engine cooling ducts. That cooling airflow going all the way through the car. We can see some of the airflow that we're monitoring going down the brake cooling and in to cool the brakes. And then we can also see some of the strakes creating these vortexes that helps to light up the underfloor and create that downforce that we're looking for. So we can also view similar going through the car. So we see the wing sitting in that clean air, and as we cut through we have the roll hoop comes into effect. So we move the wing rearwards and upwards to stay in that clean air and work as efficiently as possible. We also create this nice low pressure zone, this buffer, to keep the diffuser flowing nicely through the car. So here we have some of the forces exported from the CFD. So we can see a lot of the runs that we did with the A1 were at 110 miles an hour. We're looking for a usable level of downforce, so 110, a sensible corner, 120, 130 also measured. We see the downforce of 6,500 newtons or 1,400 pounds and the drag of 1,700 newtons or 390 pounds. This gives us a total efficiency, downforce over drag, of 3.7 to 1. Every newton of drag we have 3.7 newtons of downforce. This gives us a good comparison to some other cars. So a GT3 would be looking between 2.8 to 3 to 1 depending on the body shape of the car. LMP2s around 5 to 1. IndyCar in their street circuit configurations generally around 6 to 1. And Formula 1 7.5 and up. So the A1 sits somewhere between a GT3 and an LMP2 car in terms of its aerodynamic efficiency. And we can see as the speed increases, as does the downforce. But the main target with the A1 was a usable downforce for most drivers and for most circuits. So 110 miles an hour to 130 miles an hour is where we tried to optimize our aerodynamic forces. So as we can see, 8,100 newtons or 1,700 pounds of downforce. So this is an extra vertical load of almost the same weight as the car. So at 130 miles an hour, the vertical load is nearly double to what it would be static. However, we do not have to accelerate or decelerate that force. So this is why downforce is so useful to us. We have that extra vertical force that's pushing the tyre into the ground, but we don't have the extra inertia associated with that force.